Well, hello there everyone, and welcome back for the third time for some code generation. Let's get my visual there out of the way. And let's also make sure I have my audio settings somewhat decent. So, this is the third stream in a pretty short time actually, in which I plan to cover code generation from node graphs to native code. This is turned into a proper trilogy. I wasn't actually planning on streaming today, but I think this might be a pretty nice way to kind of cap off this work for those of you who are interested in seeing this thing, because I'm thinking I'm actually about to come to a sort of like a logical close for the work. For the time being, it's not complete, but it's basically good enough that I can use it in the upcoming pre-alpha 3. And so today we will try to actually get the work into such a state that I can actually ship the runtime code to you guys in the next pre-alpha. So if you missed the previous two streams, I did one yesterday and I did one a few days ago. What we're doing basically is we're taking the node graph based particle effects that we have in the game, such as this cartoony smoke effect thingy, and we're converting them into native code for better performance. So we're generating Zig code out of this, and we're now at a place where I actually have all of the effects except this big smoke pillar thing here actually running as native code. So for example, this smoke or dust effect after the car there is running as natively compiled Zig code loaded from a DLL, but it's built based on the node graph in the editor that we've used for all this time. In the last stream, I did some profiling at the very end, and I wasn't very happy with the performance of the new graphs, because essentially the reason I'm doing this is to get better performance out of the thing, because the interpreted graphs aren't super performant. The thing was kind of like never meant for particle effects anyway. It was originally designed for audio processing as well as high-level mission scripting. So things where you have like maybe a few cursors or something running simultaneously in an effect, but not like 100 or several hundred cursors running in an effect like they do for these particle systems. However, I was being kind of a dumbass yesterday, and I didn't realize that I was profiling the native code compiled in debug mode in particular for the particle systems. So after the stream, I experimented with the optimization flags a little bit, and I found out that actually we can get a whole lot more performance out of it, unsurprisingly, if we just compile it into release fast. So here we have here's just a screenshot of the profiler from yesterday. So here we can see this is milliseconds. So this is about the 1 millisecond line. This is one of the profiling runs that I did, where I ordered a few of the cars to drive around the map, which causes them to spawn a bunch of particle systems. And you can see that we're hovering at about 1 millisecond here. Then it kind of like dips down when those cars arrive at their destinations and they stop. And yeah, I wasn't super impressed with that. Neither was I impressed with this thing. So this is now the debug a debug code. And we can see we have a new line here. We have this teal colored native node graph update. So this thing that sits kind of like in between. And we can see that actually it kind of like bounces up and down all over the place. Reaches some of these like very, very high peaks and then falls down again. And then we have this one line here, which is the lighter blue line, which is sitting at a pretty constant, what is that? Maybe like, it's about half a millisecond. Well, that constant line is actually, it is that smoke pillar effect that we're going to try to nativize today. And the reason it is more or less constant is because the effect is more or less constant. Right, this thing is just like sitting here, spawning this smoke and these embers, and it never stops and it never starts. And so that is that's the last thing that we still have if we want to actually make everything native. And so it's this line here, right? It just like bounces up and down every now and then, but it sits more or less at like 0.5 milliseconds. The thing that I wasn't very happy with was this teal line that just goes up and down like crazy. And of course this was the debug code, I later realized. So here we can see what actually happens if we compile it with release fast. Now we can see the teal line is like well below this half millisecond of this smoke pillar effect. So this was the kind of speed increase that I was hoping to see. So happy to report that yes, it was just me not really knowing what I did yesterday, and we are actually seeing the sort of performance increase that I was hoping for. So that's great. That means that I haven't been wasting my time with this basically. But we still have this one big effect here that we need to do something about, because it is one of the heavier ones. Of course, we can run the game without that, without having it nativized, and we've been doing it successfully for a while. But if I can get that smoke particle pillar there to be nativized, then I have all of the effects in the game nativized, and I think that's a pretty nice goal to have for this. There's still some work to be done here on the actual like workflow experience of making these things and compiling them. You kind of have to copy paste code around a little bit currently to make this work, but that's something that I can look at later. I have so many things on the actual game that I need to work on before I can release pre-alpha 3 that I'm thinking if we can just get that to run natively, that would be sort of like, you know, proof enough that yes, this actually does work. So let's try to do that today. Let's try to get that thing nativized. And I've actually done quite a lot of work on that already today. Let's go and have a look here on the tools side. So here we have the smoke pillar detail. This is a pretty massive effect actually. And we can open a preview here to see it. Blip. There's the thing, there is the thing. Because it's a pretty big effect, sort of like physically as well. And yeah, we have these lines here that we're actually going to come back to in a little bit, because the lines are kind of relevant to what we're going to be working on today. So here we have the effect running in interpreted mode. That's why we can see it here. And we need to basically make this thing run in native mode. Now the work that I've done today is I've actually gone through and figured out all the nodes that we have here in this effect. You can see it's a pretty massive one. It's probably like actually way too complicated for the visuals that we have, but it's a pretty good test case anyway. All of the node except one, and it is in fact exactly this thing that we are looking at here. So let's see if we stop the emission of one of these guys. Now we can see that okay, we have these lines here, and the smoke particles actually kind of like follow those lines. Because we kind of want them to sort of like look like they're blowing in the wind, right? We can take that away as well. And these lines are made up of cubic Bezier splines. We have just like we have a few of these emitters here actually. So if we take, I think we have 4 of them. Oh, cursor to particle map already contains an entry for the given cursor. That's not good. Let's see if we can run that again. No, we can't actually. Huh. That's interesting. This is not actually the native code now. This is something else, but that's an interesting crash that we have. See if we undo all of that and we play it, and now we can see it again. What if we like disconnect that and we get the same crash? Here we get the same crash here. Interesting. So this is something with the interpreter actually. It's probably something I'm gonna have to figure out at some point, but I'm not gonna do it today. I am, however, going to just take a screenshot of this thing so I can remember, you know, where to actually, how to actually reproduce this issue. So, you know, something like that. Save that, shut it down. Let's just leave it. I don't think you need to save those specifically to have that. Maybe you do actually. Maybe you do actually. So let's do that. So it's basically like this thing and save. Yeah, save it there. And there we go. So yeah, that's an interesting thing. I've never seen that actually happen before. But much more related to what we're going to work on today. These paths that they are following, they're cubic Bezier paths, and they are, in particular, if I can find them, they're these nodes here, JSON curve path. So you can see it, here's actually JSON data. This was just because I was in a little bit of a hurry when I actually made these nodes about a year ago, and didn't actually put in any fancier UI than this. But you can basically like specify a list of points that you want to make the cubic Bezier out of. So we can add like one more point here probably. I don't think I've ever like authored these things in here, but like let's make it like 150 and 0. So that should put another point like right above the thing, right? So now you can see. So now the curve kind of goes the way we already had it, but then it kind of puts one point right above the center. Now the smoke is kind of like following that at the end there. That sort of thing, which of course doesn't look very good, but still you get the idea. And this is the only node that actually doesn't generate any sensible code. So here we have the code generated for this thing. It's actually pretty huge. It's like 6,000 or something lines. Let's see, 6,000, almost 6,500 currently. We do have this kind of thing though. But yeah, we have 133 nodes in the thing. And so if we look for JSON curve path, so here we have JSON curve path node. Currently it just returns a 0 vector. And so this thing has two outputs. You have a position and a direction along this path. And you give it a t. T ranges from 0 to 1. And so we're gonna have to make this happen. And if we do that, we should at least be able to, you know, try to play this thing as native code, which is exciting. And I think, if we go and have a look here, I actually have it already here in the Zig solution for this. You can see this is not submitted or anything. I just put it in here and copy paste the code here. We can actually already build this thing. You can see it builds. And now we're running with release fast, or building with release fast. So that's cool. Yeah, here's some unimplemented stuff. But that's that's a good get particle data node. Doesn't have everything implemented yet. But that's neither here nor there. We can actually already build this code, which is nice. So we shouldn't be very far from actually being able to run it. So I was thinking today, okay, how do I actually want to make this happen? Because the way it's done on the C++ side, which is the interpreted version of this. Go have a look here at this. That's not the correct node. It is called JSON curve path node. So here's the JSON curve path node. It's not a very big node, sort of code-wise. But that's mostly because we are using something called a curve path object, curve path 3D. And this curve path 3D has a bunch of functionality built into it, which means that the node doesn't have to do a whole lot. It still does a whole lot, like at runtime, but we don't have to have a lot of code here in the node. We just use one of these curve paths. Good mornings to and welcome to the stream. It's not quite morning where I am, but good morning to you. Right, so curve path here, it constructs a smooth curve path from the positions. The positions are, of course, the things that we looked at here, like these things. That's the list of positions that we feed to the thing, and those positions we get from the actual data stream here when we create this thing. So we construct a smooth path from them, and we build a so-called lookup table. The reason we build a lookup table is because these are cubic Bezier curves. And if you watch the Freya-Holmer's video on cubic Bezier splines, you know that you can't actually like sample the things at a fixed rate unless you do sort of like build a lookup table and then sample that lookup table. There's no sort of like mathematical way to make sure you traverse a Bezier curve at a fixed rate, especially if you have them built up of several segments. It can be really tricky to do that. And so we do all of this at runtime when we create the node. And I was thinking that's kind of stupid. If we always sample when we're building the lookup table, we always sample use this sample distance and this t step. We could just do all of this offline, right? So at the end we would end up with just the lookup table data in the runtime data. Now that's going to be more data than those points, obviously, but shouldn't be that bad. So we should just be able to do that, all of that already in the editor, and that way we could just do the lookup table sampling, which is down here. This is what we do when we actually want to get like a position, either a position or a direction. We just sample the lookup table. The lookup table is quite simply like a linear search here. I have to do comment here to change this to a binary search, but this has actually never been an issue for me currently, so I just haven't done that. Might have to do that at some point. But yeah, we're just essentially like finding the correct sample and then doing some remaps and some lerps, and we normalize the direction. We get out the position and direction. So I'm thinking this is the only code that we're actually going to put into that SIG node code, right? If you can make you can build all of this data, this lookup table data, on the editor side, then we don't have to do the building and the sampling and everything. We just do the actual sampling that we want to do for the end result. So that's my plan. And so how do we go about doing that? Well, it just so happens that the code in here for the curve path should be somewhat easy to port to C#. If we do that, port this to C#, we can just do all of this construct smooth from positions on the editor side. So let's see what we actually need to do there if we were to do this. Start with a list of positions and position count. So we have that because we already looked at them here in the editor. It's like those points there in JSON form, but we will read them from JSON. We actually already do. And then we basically check, okay, is it just like a two position thing? Then we know that it's a straight line. If it's not a two position thing, actually it's not necessarily a straight line. It can probably, well, yes, actually in this case it is. Yeah, it's a straight line if we just give it two positions. If it's not just two positions, we do a little bit of like memory figuring out here. We have some in place buffers. These are 16. So if you're trying to create just a very, very short path, or a path with very few points, you can just use the in place ones. Dynamic buffers are needed if we go above that, right? So above 16, we need dynamic buffers, and then we allocate them. What do we do then? Then we do compute control points. You can see them. I'm taking this from some Java code that I found on the internet under the MIT license. So yeah, we need to compute the control points, which is all of this stuff. Shouldn't be very, very tricky to port over. After that, we init the curve segments, and then we delete the dynamic buffers. We calculate the length of each segment, and we calculate at which t values of t the segments start and end, and then we're basically done. And then we have a curve path in memory. The next thing we need to do is we need to build the lookup table for that. So this is the sort of like the heuristic that I mentioned, that like if you want to move along a complex cubic spline at a fixed rate, you kind of need to build a lookup table for that. And so this guy actually has two sampling methods. It has sample Bezier, sample underlying Bezier curves for position and direction. This gives exact values for the given value of t, but sampling the path many times with an increasing value of t is not guaranteed to return positions equally spaced from each other due to how Bezier curves behave. This is the problem. And like with an effect like this, you want these things to like move at a fixed rate along the curve. Then of course you can, like, if you don't want that to happen, you can actually like modulate the t yourself. But if you just increase it linearly, you expect the thing to like move linearly along the curve, right? And then we have the sample lookup table, which is, you know, the same thing, but it's an approximation of the mathematical values. So when we build the lookup table, we actually use the sample Bezier for that. And then we do a little bit of bookkeeping here. And the last sample at 1.0, yeah. So this sort of thing, if we port this thing to C#, then we should just be able to do all of this beforehand at code generation time. And we basically just generate code that contains these segments. Or rather, I guess, yeah, lookup table is here. So lookup table is here, yeah, lookup table work sample. So LUT sample as a position, a direction, and a t. So it's very simple when we arrive at this point. So that's my plan. And if we do that, then it should be a pretty simple thing to just sample that from the zig code, and we should have everything we want. We need to have to nativize this guy. So how about that? Let's have a sip of coffee and then figure out how to get started with this. So let's shut this down for now. So the thing we need to do, even before we can do this curve path 3D, is we need to implement cubic Bezier curves in C#. So this is the thing that actually does the math, right? Each segment between 2 points. So if we have a path which consists of like points like this, there's 1 point, there's 1 point, and let's say here's 1 point, and then the curve path kind of like runs through these things, kind of like smoothly constructs this kind of curve here, and those things kind of like, if we use yet another color here for the control points would look something like this, right? Like this, and then we have another one maybe there, and then we have another one there, something like this. So this is a cubic Bezier that runs from here to here, and there's another one that runs from here to here, between two of these points, and that forms one segment of the curve path. And so each of those are one cubic Bezier curve. And this is actually templated. I don't think we're gonna do the templating on the C# side. We're just gonna work with 3D cubic Beziers, just straight out of the box. So let's start with that. Let's implement this or port that over to C#. I'm gonna move this off to the side so then I can reference it. I'm gonna go to the tools solution, and this thing would probably go in my generic tool, C# tools library, which is called basis tools lib. This just contains like a whole bunch of things. Among other things, we have the 3D vectors here, like this. So let's make sure we have a curve 2D, but this is not the same. It's not the same thing. This is a completely different. It's still using actually cubic Beziers because it has tangent in, tangent out. But this is actually something that's used for the curves that you can draw. I think it was last time I actually ported one of the curve nodes. And this comes from like code that I originally ported from X and A. That's not the correct thing. So let's just add a new file here. Class. We call this cubic Bezier curve, and let's call it 3D, so that if at some point I need to, I can quite simply have a 2D one as well. Right. So what do we have? I have just some vectors: start point, tangent, endpoint, tangent, get derivative, get point. This looks actually super simple. So let's start with that. We have vector 3D. Yep, there we go. So we have start point. We have start point tangent. And we have end point and end point tangent. We need some probably like properties for this. Let's make a public vec3. Actually, we can probably do this. Do get set, and we initialize them to like vec3.0, right? Something like that. Same thing with that. Same thing with that. Same thing with that, and then we use capital letters for these guys. Right, and they need to be public, of course. Like so. And then I guess the other really important piece here is, well, first of all, actually, we should look at how does this curve path 3D actually like set those values. Does it use like set, or do like curve? Yeah, it uses set, which is another way of actually setting those. So let's implement set as well. Set is also super simple. Collapse those together. It's quite simply just the same thing, but as a separate function. Let's have those as well. So we do public public void set with a large capital S, I guess. And then we have these sampling ones, which are like arguably the most important ones. Let's have those. Copy them over. We do public vec3. Right. Debug assert, right? Isn't that how it works? Debug. Probably need some. No. Isn't that what it's called? Maybe it's not. There's one at like system diagnostics. Debug assert. Yep. We can use that one. Oh. Something like that. And then we have vector3. So I think this math should basically just be the same. But of course we don't have those small m's there. I think I have all of the like operators overloaded and everything for these guys, so it should basically just be the exact same code. Something like that. So the derivative, of course, is like the direction. Get the first derivative of the curve given a value t, which goes from 0 to 1. And here's to get a point on the curve with the given value t, which also goes from 0 to 1. So these are like the most important ones. I think this might be everything we need here on the cubic Bezier front. Maybe we can do using system diagnostics. Diagnostics, like so. We can shorten these a little bit. This is an interesting task that I'm doing right now because I'm bouncing all over the place with this. I'm writing in 3 different programming languages, or at least 2. So this is C#, this is the tools side, and of course we're going to do the code generation also in C#, but we are generating Zig. And I think ideally I'd want to actually change the JSON curve node, the interpreter version of it as well, which is C++. So it's just jumping like crazy from language to language and project to project just to get this thing actually up and running. That's pretty interesting. Cool. I think we have everything we need for now. So let's leave this as it is and add more stuff to this if we need to. And then we go to the curve path itself. So let's call it curve path 3D. And this guy is more complicated, but not necessarily like a whole lot. It's longer for sure. It's not necessarily that much more complicated. Let's see. So we're gonna need to have construct smooth from positions, and we're gonna need to have build lookup table, and we're gonna need to have sample Bezier and sample lookup table. Get raw lookup table sample. I don't know where is that even used, or is it even used? It's used here apparently. So you can just give it like an I, and then it gives you back those things. That can be pretty handy, I guess. We probably don't need the serialization and deserialization stuff, nor do we need the debug drawing, nor do we necessarily need the calculate segment bounds. Where's that used? So you want like bounding boxes and things. You can use this thing. Used to calculate the nav mesh area using some of these things, but we don't need that, so we can skip it for now. Let's not spend like more time on this than we need. And just do the ones we need right now. Have you read Sebastian Aaltonen? Yes, I have. Some pretty interesting stuff, and it just shows you how sort of convoluted the whole GPU landscape is. Yeah, I'm kind of hoping that some of the IHVs read it as well and get some ideas from him. At least get, you know, inspired to make things simpler. Oh yeah, it's kind of a monster of a blog post. So I kind of skimmed over some of the areas in there, but yeah, it's interesting. Interesting for sure. Rightio. Yeah, actually, I kind of know some of the people from Hype. I've worked with some of them before because, of course, they are also a Finnish company. So small world and all of that. Right. Okay. So curve path 3D. Let's just go. I'm gonna bring this over. We're gonna see here. Okay, we have sample Bezier. That's important. Build lookup table. Construct smooth from points. Sample lookup table. And then we're gonna skip those other things. So let's just try porting some of these things over. Curve path 3D. So the first one would probably be these two. Let's get them over. So of course we don't have any pointers here. We don't have any const. Unfortunately, you might say. All of these need to be public as well. Public, like so. Float, right? So we just need to return something here so that make the compiler happy. Then we have the most important ones, arguably these guys. Sample lookup table. So here we're using references. Gonna have to port those over to C# references to make it work. Whoops! What did I do? That was strange. So this would be like, what is it? Ref vec3, I think that's how you do it. Something like that, and same thing here. I'm not even a quarter through it. Quite a read. Yeah, it is. Yeah. And I'm not sure like everything there is really relevant to understand, you know, the point that he's trying to make. But it's simultaneously like a fascinating deep dive into the history of GPUs and you know whatever came before when they weren't even really called GPUs. When we just had like 3D accelerators. Let's see, construct, will lookup table, sample Bezier, sample lookup table. Yeah, those are the ones that we need. We don't need anything more than that. So let's keep it simple for now. Then we need some types here, and I think I'm gonna put them here at the top. So this would be like a public struct curve segment, and we have here public. Oh, should that maybe be a class? I'm not sure. Let's have it as a struct for now. This would be a cubic Bezier curve. That's a curve. We have public float. I'm not gonna do that. I'm just gonna put them here. So length public float start t public float float end t. And then we have another one which is public struct lookup table sample, and we do public vec3 position, public vec3 direction, and float is a public float t. Right. So when we construct this from positions, we are going to be constructing a bunch of these guys, and then we can sample you know, a position and a direction using this sample Bezier. It samples these curve segments. Then you can build a lookup table using this function, which also samples these using this sample Bezier, and this guy constructs a bunch of these guys. And then these guys are the ones that we are going to put into the generated SIG data for the particle system. If that makes sense. So let's look at some other stuff here that we're gonna need to port over. We have this stuff here, compute control points. So I originally ported this from Java code, which you can find here. If you want to actually construct a smooth Bezier, you know, segmented path, there's some code here that does it. Somewhere, if I remember. This might be it, but this might be something else. I think this is actually it, yeah. Yep, this looks. Construct lower diagonal vector, construct main diagonal vector, construct target vector. I think that's all of this stuff that we have here. Lower diagonal main, upper, and target. So yeah, this stuff really good if you want to actually make like a segment that looks, you know, kind of like this and not like this. And of course, Java is kind of similar to C# in many ways. But still, I'm thinking we're probably just going to take my C++ version here and use this. If for no other reason than for the reason that I'm using sort of my naming conventions and everything here. So we're going to need something called a compute buffers, probably class, because we're passing this by reference everywhere. So what do we have here then? We create one of these at some point, and we're not going to have any sort of in-place things here. This is going to be a completely offline thing. So yeah, we're going to create some new arrays and we're going to store them in a compute buffers thing. So let's copy the compute buffers struct and create it as a private class. It's going to be class specifically. And these are going to be arrays, not pointers. This time around. And they are, of course, going to need to be public. Let's make them public. That one as well. It's kind of an implementation detail, but still, we're gonna need it. And then we're gonna take all of this stuff and I'm gonna take the comment there as well. I'm gonna plonk this into the class. What happened here? Something funky with my indentation. It's really, really funky. Let's try to not mess with this. If that's okay with Visual Studio. It's not okay, apparently. Wow, this thing is just completely broken. Gamma. Should look something like this. Of course, it's completely confused now with like whatever we are doing here. So that's going to be a uint, and this is that's an array. Am I missing a cast? Maybe I am. Let's do like an int conversion there. All right. That's going to be private. Let's hope we don't actually break any of this math here, but while I'm messing with this stuff, but it should be fine, I guess. So is that the same for all of them? It's not. It's kind of similar. Let's see, uint as well. And these don't need to be like explicit references because it is a class, so it is a reference type by default. Right. Something like that, right? And so I think this is all of the hairy math done for us, really. Just make this private. I typically tend to make it very explicit whether something is private or public whenever I write C# code like this. Rightio. Take one of these separators here. Like specify that we're entering like implementation mode here, the private section of the class, if you will. So let's see if we can actually make this construct smooth from positions happen now. I'm gonna copy all of it, and it's probably gonna be just completely broken again for a while. So let's see what happens. Here we again have positions count. Well, that would be, now we're using C# arrays. So this would be positions.length, right? System diagnostics debug assert. Segments clear. We don't have a segment. What is segments? Let's have a look. Whoops. So we have segments and we have lookup table. We're gonna need both of those. Let's add them here at the bottom. I typically keep my private members. I can just initialize them directly here, and that also needs to be a list. If you've done a lot of C#, you might realize that my C# is kind of like old school and not very elegant, but it's also like decidedly not fancy, and I like that. M segments, right? Yep. That's called clear with this little capital C. Resize 1, that's not really how you do it. Instead, we're probably going to want to have, let's see, let's make a segment is new curve segment. And this is a class. Let's make that like a new cubic Bezier curve like that. Oh, there's no right. We need to have like a default constructor, right? Yeah, okay. This is the annoying thing with this. Cannot have instance property or field initializer in structs. Well, let's make it a class then. I don't care. I don't care. We don't need this segment resize if we actually add the segment there later on, and then this can all just be segment group. Set does not contain a definition for set. Did we not actually add a set? We did, but it's called set with a capital S. That's the problem here. You can see a lot of this stuff is just like actually, you know, actually the same in C++ as it is in C# when you're writing this sort of like very basic C#. Segment count, I bet that's probably an integer. So if we do positions.length here, and that's probably like an integer. We don't have any in-place things. Compute buffers, this needs to be a new compute buffers. Maybe that can be a var. Dynamic buffers, yeah, sure. Later on we're gonna have to delete them, so let's just get rid of that thing. And we jump back up here. So we are always going to have dynamic buffers here. Just get rid of all of that stuff. And here we have let's see if I can remember my C# now. So that's an array of vector trees, so it would be like this. Am I right? Yes. Seem to be right. And there's one more vector tree array, and the rest of them are float arrays. So float, new float array, like that. Right. Trying to be careful here not to like actually break this thing, right? Because then I will be very confused later on if the math doesn't actually work. Resize to segment count. That's confusing. Okay, that is again because like we're just setting these things. So okay, let's not do that. Let's just add them here instead. What is PI? Okay, yeah, it's just a separate counter there to keep track of those. Okay, that's fine. So, you know, this sort of deal is probably better if it's just a var. And this would be that would be a segment, and calculate the length. Right, so we're setting the curve, then we calculate length and start t and end t, and we're doing the same thing, or we're doing that actually here, so that's fine. Yeah, it's actually better that this is a class, because that way we can do things like this. Just take, you know. Well, I'll show you when we get to it. It's fine. It's fine. I'm gonna convert all of these to integers rather than unsigned integers. Here we are working with unsigned integers though, and maybe that is fine, I'm not sure. I think it's probably fine. Yeah, there's some integers there though. It's the same thing in the C++ version. Yeah, it's peculiar. We have like unsigned integers here, then we have integers here. Okay, so let's just YOLO this and convert all the unsigned integers to integers. We're not gonna have that many points that we actually need to like be afraid of the range here. It's not gonna be an issue. In place buffers we can just completely delete all of those. Bye bye. And yeah, like I mentioned, we don't need that. And here again we can have a var segment new curve segment segment.curve set with a capital S, and then we add that to the segments. Right, and then we can resize that thing. Okay, and here we have for each curve segment in segments, not that kind of eye, that kind of eye. So just like small little changes here and there, and then the thing compiles as C#. Take that away. Here we have some const that can actually remain. Math clamp. Okay, do we have any sort of... We have basis math helper clamp min and max. Yeah, that looks good. So we can just take that stuff and clamp it using that. There we go. Oh, one extra. There we go, and then that would be an integer, and that's it. And since these are now references, we can actually do this, and it's automatically a reference. So that's nice. Yeah, very nice, very nice. Okay, that would be that. Now we could essentially like already construct these guys. Can't quite sample them quite yet, but soon. So let's maybe do the sample Bezier, kind of like do them in the order that we're going to use them. So now that we have this working, now we should be able to sample them using the Bezier sampling, and that is quite a small function, as you can see here. Having written quite a lot of Zig lately, my brain goes like, hey, this how does this actually compile? Because like in Zig, this would be a constant. You can't actually assign to a parameter like this. But of course this is not Zig, so you can do that, but yeah, I tend to not do that these days. Even in languages where you can do that, because you can do it in Zig. And I'm sure you can do it in like languages like Rust either, but I'm not a very big Rust guy, so I'm not exactly sure. So here we probably can we actually have a constant? Pretty sure we can't have that. No, we can't. Segments, that would be length. No, that's count, isn't it? Yeah, it's count. It's count because it's a list. So lists have a count, and that's actually not a function, it's a property. In lists it's called count, in arrays it's called length. It confuses me every time which one is which. Then we need some more clamping. Math helper.clamp. Oh, that's a remap. So math helper remap float is what we want. Boink. There we go. Everything else seems to at least not complain. Here we have something that does complain. What is this? Oh, we have a stray parentheses. parenthesis. What is like the singular of parentheses? Cool. So find the segment for the t and the t for that segment. TS, and then sample the position and direction. Yeah, exactly. We find the segment and then t for the segment. So like the t value within that segment, and then we sample at that position, and then we return. That's good. Cool. Okay, and then we do. Well, we can do the lookup table thing while we're at it. So it shouldn't be very tricky. This guy probably needs to be a class as well. I'm just gonna make it a class now and not have to care about it. Okay, so if lookup table count is 0, then we return. Otherwise we do int and we do count, and that is something like that, and that is something like that. That would be math helper remap float lerp. Do we have a lerp thing in here? Lerp? No lerping. Is there a lerp in the standard library of .NET somehow? Here's mathhelper.lerp. Yeah, this is. I don't think this is my math helper. What are we lerping though? We're lerping a vector 2. Yeah, we're lerping a vector 2, and that's also lerping a vector 2. Or vector 3 actually. Yeah. So the way this works in C++ is probably that I have an overload for this, and then we lerp the actual components separately. Okay. Well, we can add those things to the math helper. You can see it's a pretty small one actually. Found here, but it's fine. It's fine. So let's add the lerp and let's add the smooth step while we're at it. So this needs to be public static. And then we have the vector 3 lerping. So public static vector 3 lerp, and then this would be just a, I think, by value kind of situation. There we go. So now we should be able to lerp those guys. Math helper dot lerp and math helper dot lerp. There we go. And again, we should perhaps change this to a binary search at some point. But at least like in C++, this has never actually come up in my profiler or anything. So at least with the kind of data that I typically handle, a linear search is quick enough. Okay, so then we have the build lookup table left. Shouldn't be super tricky either. Let's see what we're actually doing here. Alright, so we have a profile block there. We can take that away. Float distances. So this would be a list of distances, and we need to initialize it to something. And then we have lookup table clear with the big C. We have a work sample. Okay, that probably doesn't really make any sense because this is a class now, but whatever. So how does this work? So we initialize a work sample Bezier. So these need to be like ref, right? Something like that, and then that would be a large S. And work sample T, use of unassigned local variable work sample. Yeah, this would need to be new loot sample, something like that. Now, the important part here is that, like, since this is now actually a class, we need to create a new one when we sort of are done with this loot sample. Unless we actually keep it as a struct. We can do that if we want to. It could be a struct. And if it was a struct, this would work sort of like more similarly to what we have been using before. Maybe we'll try that. We'll use it as a struct like this. Here, where we are pulling it out of the list, this will now make like a copy because this is a value type. Well, that's probably completely fine. So let's try that. Let's keep it as it is for now. So that needs to be a large or capital S. That needs to be a capital S, and then these need to be like ref, and ref. Like that. And then we have some pushback things here. So they just get changed to adds. Add. Is there something else here? There's some more pushbacks. I think the rest of this should be pretty good. Yep, that looks good. And then we have like a for each in and lookup table. This would be count, and then this would be a normal or a signed integer. I don't know what a normal integer is, but a signed integer. What's the problem here? It's not a variable. What? Right, okay, so now that this is actually like a class, or sorry, a struct, that can't be done. Now it probably can be done. Yeah, now it doesn't complain about it. But if we make it a struct again, now it complains about it. So the thing we need to do here is like we need to get the thing out of it. Temp sample is, you know, that, and then we do temp sample dot t is that, and then we actually assign it back. Something like that, right? And that should be it. That should be basically the whole thing ported. Can we build this now? See, it does build. Okay, cool. I wonder if we can actually use it now. I don't think we need that thing. Let's get rid of it. All right, so What we can do now is we can go to JSON curve path node, and it's probably not actually that one, it's the other one, it's this guy. So convert to Sprinter. This is the code that converts this node into the representation that the interpreter needs. And here we can see we have like validate JSON and we have get positions, and these two guys. Yeah, validate JSON calls get positions from JSON. Get positions from JSON just like does a deserialization here. And get positions actually calls get positions from JSON. Okay, all of that is fine. We do, however, like do this twice here, which is a little stupid. Even here in this convert to Sprinter, here's the new code. Here's what we're going to implement. The new stuff. But let's not get ahead of ourselves. Let's actually let's redesign this a little bit. I don't like the way I've done this at all. So this can be just like a vector array that we call toArray here, because never want to modify that. Validate JSON can still do that stuff, but now it needs to be called, like I said, it's called length with arrays, so that's why it complains there. And then we get like positions here, and we call get positions from JSON. And it's actually called node.json data here. And I'm gonna just quite simply do like if positions is null or positions length is smaller than 2. That's basically the validation. So we can just use the same array here. Then we push those. Oh, that thing is a list. That's why I have it as a list. Okay, that's stupid, but whatever. Yeah, the serialization is a little. Okay, whatever. Let's not worry about that. We're still only gonna be using it once though. We're still only gonna get it once from JSON and then do the validation with it and then push it all at the same time. That's better. We've been sort of stupidly deserializing it twice from JSON just to do the conversion. That's stupid. So don't do that. And then we do the same thing here basically. I mean, we could like potentially do like a validation that would like return the list as well, but nah, I don't know. This is a public static pool. I think it's actually used elsewhere, so let's keep it as it is. We do the same thing here. Invalid position list in JSON curve path node. So the code generation fails if this thing isn't valid, which is perfectly fine. That is a perfectly valid thing to do to fail the code generation. And here is now where we actually want to do this this curve path of ours. So let's do var curve path is new. Maybe I should get like, maybe I should make a function for this. Let's make a private static. Let's make it return like a vec3 array get lookup table samples. Right, so it should actually probably be one of those. So it should not be a vector3, it should be like, what did we call it? Here, lut sample. Yep, this would be a curve path 3d dot lut sample array. get loot samples from the vector 3 positions. Something like that. Right. Samples. Get loot samples using positions. And then in here we can do curve path is new curve path 3D, and then curve path construct smooth from positions, and we give it the positions, and we do curve path build lookup table, and maybe we should look at what the JSON curve path node already does here on the C++ side. It uses those values. Sample distance is the first one, I think, and then t-step is the second one. There we go. And now we can just return curve path, lookup table samples. Okay, we need like a property for that or something, right? Loot samples, and then we do get. I think this is how we did it. Lookup table to array. Something like that, right? Loot samples. There we go. So now we have the samples. This is the stuff that we can now actually just write into the code. Right, and we can do the same thing we did with the actual curve node yesterday. So this is something that I actually did yesterday on stream. So here if we go have a look here on I think it's this one, for example, has a curve node like this. We add it as a declaration. And now we are, of course, in Zig, so now we have switched programming languages. We're gonna spend most of the rest of today's stream in Zig land instead. This is not like this is not a slice. This is actually like an array literal, I think is what this is called. But basically it's a list of Sprinter curve 2D points. Right, and so we need something similar. This has been generated from the code, so we want to generate something similar to this. And the code for doing that is basically like this. But I'm thinking we might want to actually like define the type here directly in the node. That might make sense here, at least as for this sort of first kind of like test. So let's go into smoke pillar detail and find the JSON curve path node. Looks like this. So the thing we're going to generate looks something like this. We're going to have a list of something, but that something needs to be defined first. So let's do const loot sample is a struct, and the struct has where's the thing? There it is. Whoop. It has a position, it has a direction, and it has a t value. Right. So position. This will be a Sprinter vec3. It has a direction. sprinter vec3, and it has a t value, which is a float 32. Something like that. So now that we have this declared here, now we can create this kind of list of it. Let's just call this samples, and it's a list of these guys. Right? And so it is quite simply a lut sample. Position. I don't exactly know what to do here. Let's do a sprinter vec3 init 0, 0, 0. Direction is basically the same thing. And t is just like 0, whatever. Dot t, right? Like this, and then we can have a bunch of these guys all together. So this is the kind of code that we want to generate. The thing that's going to hold the actual path. If that makes sense. Right, I'm gonna go get a glass of water because again I've been talking so much here. So I'll be back in like 1 minute. Alrighty then. Just looking back here at the chat and the stream, we're finally getting some viewers here. Welcome everyone. Even though we're not that many currently, but still it's increasing. It's increasing. That's nice. So what we're doing here is we are trying to generate the code for the last node, at least the last node that I know of currently, for running all of the particle effects in the game so far using native code rather than being interpreted. So let's see if we can make this sort of thing happen here by generating it from C#. Actually, I think we're pretty close to doing that already. So let's copy this over. So this is the sort of thing that we wanna make happen. Chup chup. No, don't break my code, please. Comment it. This sort of thing. And all of these lines here are essentially like what I consider to be a declaration in the code generation. So code gen node add declaration. These are quite simply just lines of whatever you want. So the first line would be that. The second line would be this, including the indentation. If you want it to be nicely indented. Oh, we need one more. One more to wrap this thing. Like so. There's our type definition. Or declaration, whatever. And then we need a start and an end for this thing. So that's already good. And then we need basically a for each loop var sample in samples. And we're gonna do code gen node add declaration. And we're gonna do it like a string format, I think. And then we need sample. Okay, so now we could maybe do something fancy here to make this a little nicer, but I don't know what that would be. So I'm just gonna do it the stupid way, because I can't be actually arsed to look into how to do this in a smart way. Basically, what I'm thinking is that there's probably some way of like not having to repeat this position and direction business here, but it's fine. It's fine. And then we have this guy, and actually we want to go all the way over here. I need some width for this. So that would be probably like, I can never remember the syntax for this, but we want basically like at least 3 this thing on at least like 3 digits of precision here, maybe even more, but let's go with 3, like so. I want the same for this guy, but it's gonna be 0, 1, 2, 3, 4, 5, and then this is 6. There we go. Format string contains invalid placeholder. Yeah, it's these things. We need to double squiggly them. Otherwise, it's gonna get cranky with us. There we go. Okay. So what we can do now is quite simply just run this and open the effect and see if we can get some code out of this and see how freaking long that is. It's possible that it's just like super long with super many points, but we'll see. So let's do JSON curve. Find, here's the JSON, and you can see, yeah, it is. It's pretty long. It's pretty long, and you can see here the t value increasing from 0, going all the way to 1. But it's fine. We're getting some stuff out of this, so it's probably fine. I mean, we're redoing the code generation every time we move this, and still pretty. There's a little bit of jerkiness there. That might be something else. That might be just the fact that this graph is so big. But yeah, it should be faster. It should be faster. I need to like actually optimize my tools. Anyway, I don't think we need to really consider that right now. This is of course like quite a lot of data when you look at it like this. But like compiled down into the form that it's gonna take at runtime, I don't think it's gonna be a big issue. We should have another one, or at least one other one. Yep, here's another one. And there's one. And there's one. So we actually have like 4 of them at least. Here's probably just, oh, here's a 5th one. Yes, we have 1, 2, 3, 4, 5, 6 actually. Okay, six of those. So considering that, I'd say we're not like super slow actually generating this stuff, but it might have to be optimized later on. So anyway, now we have the data in a form where we can actually read it at runtime. I wonder if I should actually be a little smart about this thing and split this code into two different files. So we would have like the main file, which would be just the code, and then this thing would actually include or import another file which would have data like this. That might be something to think about for the future, because it's, if you just want to look at the code here, it's kind of annoying that you have these pieces of data here in between. Of course, this whole node is kind of strange. This JSON curve node is kind of a weird thing, which is only used here in this one node, or this one effect. Now that I think about this, though, these lines are so long that we might just do this actually. Take away the comma there and just add that thing all on one line. That's probably fine. We can add a new line there in between. So then we have the code generated. Now we're gonna need to have some way to actually sample this thing. So basically, we need to take this data and we need to handwrite the sampling logic for it, which shouldn't be super tricky. I'm going to take one of these JSON curve nodes, number 37, why not, and just copy number 37, and we're going to copy it into node 37. It's right here somewhere. There's no node node number 37. Copy it in here, and we see, okay, get position, get direction. These are the two functions that we are going to want to read. And we read it. Oh, what is happening? We just do the code. It's just yanking out. Yeah, look at this. We just do the code. It's like bugging. If I scroll. Oh, it's probably like. That's interesting. It's probably reaching some limit with these sort of like type helpers. It just like gives up after a while and just shows these remaining lines without the type helpers. That's like inline. What are these called? Well, anyway, these gray things here that aren't actually part of the code, but are like things that Visual Studio Code gives you. I think there's probably some like maximum number of those that it kind of wants to show you, and then after a while it goes like, nah, I'm out. But it has this weird effect here. Anyway, let's not care about that. What we want here is a way to, given a t-value, that comes in on this pin here, return the position here and the rotation, the direction here. That shouldn't be too difficult. Let's figure it out together, shall we? So basically what we want to have is this sample lookup table. And it is quite simply this code here that we're gonna need to port over to Zig. And our lookup table is basically like this. Lookup table here is this positions, or samples is what it's actually called, samples. The rest of the stuff should be exactly the same. Yep, that looks good. Okay. And these two return vec variants. They essentially return 3D vectors, always. So I'm gonna move that off to the side. And with a little bit of luck, this is the last piece of the puzzle until we can actually, or before we can run this in the game. So let's see. Exciting. I'm gonna create a function here that we call sample look, sample lut, whatever, sample lut. And how will it work? Well, it will take in the t value, which is a float 32. It will take in a position. Maybe we should make like an optional pointer to a sprinter vec3. And it will take it in an optional pointer to another sprinter vec3, which is the direction. Like so. So then we can give null for the one that we're not interested in. So that's the C++ code, which of course won't work. Lookup table empty. So we can do like if samples.len is 0, then we return. And then we can do what can we do? We can probably do something like for samples, and we get the sample and we get I. And then we don't need that thing. So then if sample is larger than t, check if I is 0, then position is that. Yeah, that's all good. Previous sample const prev sample. Oh, 1 second. Alright, sorry about that. A bit of family business to take care of. So, let's do points. No, samples. It's still called samples. I don't know why I keep calling it points. Something like that. And then that needs to be also a const, and this needs to be sprinter math remap float. And we don't have any f's in Zig. Get rid of that. And this would be sprinter math lerp. Same thing with that. And direction normalize is also not quite okay, but one thing at a time. So if pos, right, p then we do, and that's a pointer, so we do p dot star, and that's how we can like essentially, let's call that d dot star. So these are optional pointers. We need to unwrap them to check if they are actually given, and then this p dot star means like write to the value that is that this pointer is pointing to. So we're dereferencing the pointer, and then we need to do, of course, we need to do the same thing here. So that would be That would be that. And then we need to do the same thing here. So that would be that. And we have D star like so. And then I guess we need to normalize this, so we do sprinter vec3 normalize normalized. Yeah, we can actually just do that here. Oh no, by the way, this might actually be more elegant to do, because it already, I think it takes a pointer, this thing, yeah. Takes a pointer, that, so we can just do D. There we go. Like so. How about that? And then here we basically get the t value from somewhere. Well, let's call it, let's just have it to be like 0.5, right? And then we do let's think about this. Let's think about this. This would be vec or var variable p or position, whatever, pos is you know, sprinter math, no, sprinter vec3 0. Yeah, 0 is fine. And then we do sample lookup table using the t, and we are interested in the position, so we're giving it the address of pos. And as for the direction, we're not interested in it right now, so we do this. And then we can do return init from vector3 position, like this. Right? And then the direction would be, you could call that direction instead, and then we give this as null, and the direction we give as address of direction, and then init from vec3 direction, like so. Yeah, that's basically it. And I think that's pretty much the same thing that this original code does. It samples them both, so position and direction, like this, and then we just like write one of them. So there could like potentially be a little bit of an optimization here, if you know, if you sample the direction and position of the same t, you can sample both of them, because we're essentially doing that already, and then store both of them, and also store the sampled t, and then next time you go look. So if you first you sample position for like t, say 0, and then you sample the direction for t0, it could look, oh, did we actually already get the direction for t0 as part of getting the position, and then you could immediately return that. But yeah, we're not doing that right now. It's fine. It's fine. But okay, so now we have the logic. We've just written this inside here, and we need to put it into the code generation so that we can actually use it. First of all, let's make sure this actually builds, and it does not. Okay, let's see, what do we have? Expected type f32. Oh, we're lerping, right? We're lerping floats here, not vector trees. Do we actually have some vector tree lerping code? Lerp. No lerping. We're gonna need to lerp though. So the math library that I have here as part or available to these node graphs are or it's significantly scaled down from the one that I use for the actual game. Vec3 lerp. Yeah, this is a lerping function, so let's just take that lerper from there and put it here in this as well. Give it some nice lerpy action. That would be sprinter. There we go. So now we can do, instead of sprinter math, we can do sprinter vec3 lerp, and same thing there. Now that should hopefully work. Build. Yes, now it builds. Excellent. Yeah, I'm just kind of like bringing math functionality over as I need it for these things. The vector tree here actually looks a little bit different than it does in the main game. Here I'm using an extern struct in Zig, which means that this the memory layout of this guy is guaranteed to be ABI compatible with the C one, or it's essentially like using the C memory layout, which is important for particle systems. We're just poking at pointers directly from the C++ side. You don't want to like copy. You don't want to copy values over for all the particles. You just want to modify them in place. So it's very important to have these vector trees be extern struct. But extern structs aren't as flexible as just normal structs in Zig, so the game doesn't quite work the same way. It uses just normal structs in Zig to make the development experience a bit nicer. Okay. Coolio. So now we can take this logic here and put it into the code generation. Of course, we already have these functions here. We do need the sample lookup table function. So let's copy that and copy it over from there. So that's the sample lookup table function, and then we need to modify these two guys to actually use it. So get position is there. And again, the indentation is a bit wonky here. And it comes from the fact that we're using these verbatim strings in C#. Maybe we can do something about that at some point. But here we have now const t equals 0.5, which is obviously not good. Instead, we want to have something like this. Value pin. It's not called value pin though, it's called T pin. And there we go. Position pin, direction pin. And position pin is registered to match this get position call here, and direction is the same thing for the direction function. So that means that when someone is requesting the position through this position pin, we call get position. And we run this thing here, which does the whole sampling and everything. Cool. What do you reckon? Will this actually work? Will this thing actually work? Nobody knows, but we'll find out. So we can generate the code at least. And now if we go and have a look here at the JSON curve node, or the JSON curve path node, yes. We can see, okay, we have the data just like before. And then we have the position, and you can see const t is now being read from some pin somewhere. Same thing with this other one. What node ID is this actually? This is 37. So if we have a look here in the actual graph 37 is there, and it reads it from the curve node at 39. So that means that this t value here, which comes from node 39 and node 39, this is correct. It's good. Yeah, these will always be the same. It's just reading them from the same pin, basically. Then we have the actual logic. That looks good. Okay. So if I select all of this, select all, and then I copy it, and then I bring it over, and again, this is the part that we currently have to do by hand. Eventually this will be handled for us. Just remove everything except the very top stuff. Like so. Do we have any auto fixes? Yes, we have an auto fix here. So emit particle node, rand auto fix. Huh. Why is that? Why is that? Emit particle node. What does that actually? Oop, that's not where I wanted to go. This is where I wanted to go. Right, so the lifetime is that, or what is actually using random here in this? Ah, okay. Yeah, I know what that is actually. It is because these are using points. So if I make that like a sphere, that's number 2. That's number 86. So if we go and have a look at node 2, it's right here. We basically need to do it here, don't we? Node 2. Now the random should be used. Yeah, now it's used here. Exactly. But here we're not, because it's just a position. Yeah, okay, so that's actually a bug in the emit particle node. Let's just fix that while we're at it. So, see, here's the rand, and we only use it in the sphere case and in the box case. Yep. We're not using it if we are just spawning from a point. So I'm just going to add it there, and I'm going to add it there, and that should fix it. Basically, we don't want any of these auto fix lines to appear when we save this, if possible, because that means that we've had some unused variables or constants that Zig doesn't really like when you have that, or it just like straight up doesn't compile if you have that, and that's why ZLS adds those auto fix. Yeah, now we don't have any auto fixes. ZLS adds those for you when you save this here in Visual Studio, but of course, like, eventually I'm not gonna copy paste this stuff into Visual Studio Code anymore. I'm just gonna compile the thing that I've actually generated, so I want the code to be valid even without the auto fixes. I could run it through a Zig format though, if that is actually a good thing to have. Alright, so if I uncomment this line here, now when we run the game, it should run that thing as a native effect. How cool is that? Let's see if we go to binary. Yeah, it was like 500k, so it actually does grow quite a bit just from that data that we added there. It's a bit of an interesting observation. You might not have to sample the lookup table at quite that frequency. We can get rid of some of those lines. Alright. Alright, so there's the thing. There is the thing. It does look the same. I'm a bit skeptical every time I I do this, like whether or not I actually have the thing running as a native particle effect. And I made some mistakes in the previous streams with this exact thing. So let's connect to the game here and let's start a profiling session. And we can have a look here. Here's the Merlin update, advanced time. And here we can see that indeed we are running it in native mode, because you can see the refinery smoke pillar detailed.zig, and we can even see which nodes are taking how much time. And it is indeed taking quite a lot of time because it's a very, very heavy effect. But we have just one of them. But hey, that's cool. That's cool. Maybe we should run through the same. Maybe we should run through the same profiling session that we did with those other effects earlier, and see how it stacks up. We have everything running as a native. But that's cool. It's very cool. So what I did was I drove here and I started asking these guys to come to me. And what we can see here is that this thing in particular, the Merlin effect instance advanced time, should start taking longer, and you can see it actually does. It does. So here's some different sections. This is just the main the smoke pillar. So this is where I started driving, and you got all of my like dust particles and everything from the car running on top of the smoke pillar, and here you have those other vehicles doing the same. And now that these guys are arriving here, I'm gonna ask that guy to come to me. Come closer, please. And they are arriving, and as they are arriving, this thing goes down. Now we have just the gripper truck, which is the slowest vehicle, arriving last, and when it arrives it should go down to basically this level we had there at the beginning. Hello to you, good sir. And now we're falling down, and we are back to the same level. Excellent. Okay. This is cool. Let's shut that down. And we can compare this against the previous profiling session that I had. So here is the thing where they are interpreted. And then we have the same thing here, where they are native. And we can see that, okay, yeah, we have some spikes here. Particularly here, this section is pretty high. Goes up to like 0.4. 1.4. 1.5 actually. 1.5 milliseconds. And then it goes down. And I would say like the average of it is like sitting here at maybe 0.75 or something like that. But of course we're actually profiling this thing, and having the profiling on currently means that we are injecting the code with these kinds of calls. Begin profile sample and then defer end profile sample. And these things actually cross the DLL boundary every single time. So actually profiling these things is kind of heavy. You can see that it's inserted for all the nodes that actually have an update function. You can see here node 5 update, blah blah blah. And then we also have towards the end, where's the update function? Here it is, kernel update, and then it prints the file name, and that's how we get these file paths here, that we can actually identify which one of these effects we're looking at. But yeah, as soon as I flip off the switch that we don't insert those things anymore, they should be even faster. But currently we have a little bit of an overhead here, crossing the DLL boundary at least twice on every update, just to be able to profile them. But that's fine. It's easily turned off, just a single boolean. Anyway, this is kind of where I wanted to get today, and here we are. And yes, it is faster, even with all the effects turned on. It's not like a huge amount faster, but it is about twice as fast as it was before, even with the profiling on. You can see here that here we're sitting at roughly 1 millisecond. Well, it goes down towards the end there. And here we're sitting at roughly 0.5, maybe slightly higher here. So it's pretty nice. And we can of course make it even faster by optimizing the code further and turning off the profiling, and then even doing the batch updates that I mentioned yesterday if we really need to squeeze the last few percentages out of the performance. But that is nice, and that is basically where I wanted to get today, and we did it. So I consider this a success. And perhaps most importantly, the thing runs and it looks the same and behaves the same. You can see all the embers there doing their thing. And yeah, this effect could use a little bit of work. Could probably be simplified, the actual like node graph a little bit. But already it's running much faster than it did before. So that's cool. But ladies and gentlemen, I think we are done with this trilogy of streams covering the node graphs and its code generation for this time. I for one am happy to be done with this thing finally, so that I can move on to other things. Now I have a way to run these things in pre-alpha 3 already. We can get some nice performance boost out of this, and later on when I have a bit more time I can make the actual like editing experience a bit nicer and make it so that it can you can preview the native compiled effects directly in the editor. You don't have to run the interpreted ones and all of that. So that's neat. But now I'm eager to get back to actual game development, now that we have this thing kind of at a state where I know, yes, it works and it can be improved upon. So I bet next stream is going to be something completely different. But I think we're done for today. If this is cool, do remember to like, subscribe, perhaps join the Discord server if you want to play the game. Pre-Alpha 3 is about to be released pretty soon, and for the time being I ask you to join the Discord to get access to that. If you're not quite that eager, but you still want to keep up with updates, remember to subscribe to the channel so that I can let you know when the next video and or stream is going up. And all that remains is to wish you an excellent rest of your day. Take care and see you next time.